Today we are going to learn an important spectroscopic technique, that is Mössbauer spectroscopy. Mössbauer spectroscopy. Mössbauer spectroscopy. Okay, and today we are going to learn in detail about the Mössbauer spectroscopy. First of all, let us consider a general radioactive disintegration reaction. Okay, or a nuclear reaction where a radioactive nucleus A disintegrates to a stable nucleus B. Okay, and this stable nucleus B is first formed in the excited state, and this excited state nucleus will then come back to the ground state, that is normal B, and during this process electromagnetic radiation will be emitted. And if you are checking the frequency of the electromagnetic radiation, normally it will come under the gamma ray region of the electromagnetic spectrum. For example, we can consider such a radioactive disintegration. You can consider cobalt 57, okay, and this cobalt 57 gives iron 57 by a radioactive disintegration reaction, and initially it will be formed in an excited state. The iron nucleus, the Fe57 nucleus, will be in the excited state. This is excited nucleus. And this excited nucleus will then come back to the ground state nucleus, that is Fe57, the ground state nucleus, that is ground state. And during this process, what will happen? The gamma ray will be emitted, right? The gamma ray will be emitted here also, gamma ray. And now the frequency of this gamma ray depends upon the energy difference between the Fe star and Fe, or the excited nucleus and the ground state nucleus. Actually, if you are considering the energy difference between the excited nucleus and the ground state nucleus, it is about, okay, that is the difference between the Fe57 star and Fe57. The difference is around 2.30 into 10 raised to minus 15 joules. This is the difference between the Fe star, which are 57, and Fe, okay, Fe 57. This is the energy difference. Delta E, that is equal to 2.30 into 10 raised to minus 15 joules. So the frequency which is being absorbed, emitted from here, the gamma ray frequency which is being emitted from here, can be calculated. So the frequency nu corresponding to this energy difference is equal to delta E divided by H, right? That is equal to 2.30 into 10 raised to minus 15 joules divided by Planck's constant, that is 6.625 into 10 raised to minus 34 joule second, right? And that is around 0.35 into 10 raised to 19, okay, you can calculate like this. The unit is per second, because joule and joule will be cancelled, and the net unit is per second, and that is equal to 3.5 into 10 raised to 18 per second, or we can write it as hertz. Okay, so this is the energy, this is the frequency which is being emitted when an Fe star 57 nucleus is being produced from the cobalt 57 nucleus. because this Fe star nucleus is coming back to the ground state, and this frequency will be emitted, and this is coming in the gamma ray region of the electromagnetic spectrum. Okay, now if we are placing an iron nucleus in the way of this gamma ray radiation. For example, cobalt 57 is disintegrated to Fe57 star. Okay, and this then comes back to the ground state, that is Fe57. Okay, and during this process, the gamma ray will be emitted, and the frequency of this gamma ray will be 3.5 into 10 raised to 18 hertz, or roughly 10 raised to 18 hertz. And you suppose that I am placing an Fe57 nucleus in the way of this gamma ray. What do you expect if I am placing this Fe57 nucleus here in the way of the gamma ray? Okay, a sample nucleus. And you can expect that the sample nucleus should absorb this gamma ray, and then it should go to the excited state, right? It should go to Fe57 star. Okay, so that this gamma ray will be absorbed. That is what we are going to expect. The gamma ray will be absorbed. But normally, if you are doing this, okay, that doesn't happen. For example, you have a cobalt 57 source here, and in this cobalt 57 source, iron 57 will be produced in the excited state, and then it will come back to the ground state ion. Then the gamma ray will be emitted from here, and if you are placing iron 57 nucleus here, and you are placing a Geiger counter here just behind this iron nucleus. This is a Geiger counter. It will count the gamma ray photons coming after the iron 57 from here. Okay, so you are placing a Geiger counter just behind the iron 57 nucleus, and if you are observing if there is any fall in the reading of the Geiger counter, you can see that there will not be any fall in the reading of the Geiger counter. When the Geiger counter reading will fall like this, okay, if you are seeing a fall like this, it means that in this frequency the electromagnetic radiation is absorbed, right? But that doesn't happen, and so you actually expect that should happen, but that doesn't happen. Okay, and we are going to think what is the reason why it is not happening. Okay, so we have to consider certain things in order to understand why it is not happening. First of all, let us consider the life of the Fe star nucleus, life of the Fe star nucleus. Okay, life of the Fe star nucleus, Fe star. Okay, it is 57 nucleus. And if you are checking the half-life period of this Fe iron 57 in the excited state, okay, and that half-life period is almost to 1.5 into 10 raised to minus 7 seconds. That is a half-life period. It's a short-lived nucleus. Okay, that's why it is. Then it will immediately come back to the ground state. So, what is the consequence of this short life of the excited nucleus? Here, the uncertainty principle comes to play. You know that the uncertainty principle, uncertainty principle. Okay, from the uncertainty principle, you know that delta E, that is uncertainty in energy, into uncertainty in time, delta T, is almost 10 raised to minus 34 joule second. Okay, you know this already. Delta into delta T is almost equal to 10 raised to minus 34 joule second. And from here, we can calculate the uncertainty in energy. Uncertainty in energy. Uncertainty in energy of what? Energy of the excited ion nucleus. Energy of excited ion nucleus. Okay. Uncertainty in energy of the excited ion nucleus is delta E, that is equal to 10 raised to minus 34 uh, joule second divided by what? Delta T. Delta T is already almost 10 raised to minus 7 seconds, because half-life period of this iron 57 excited nucleus is almost is 1.5 to 10 raised to minus 7 nucleus. Therefore, we can take delta T, that is the uncertainty in time, okay, as 10 raised to minus 7 seconds. So what's the answer? 10 raised to minus 34 divided by 10 raised to minus 7. So that is 10 raised to minus 27. Okay, 10 raised to minus 27. 27 joules. So that is the uncertainty in energy of the excited nucleus. Okay, uncertainty in energy of the excited nucleus. So this is the point that we considered first. Okay, what is the point that we considered first? That is the uncertainty in the energy of the excited nucleus. We got this from the idea of life of the excited ion nucleus. The second thing that we are going to consider is the line width. Okay, line width, because the excited ion nucleus Fe star is coming back to the ground state nucleus. Okay, ground state. Then during this process only the gamma ray is emitted. So the frequency of the gamma ray depends upon the difference in energy between the excited nucleus and the ground nucleus. But we have already proven that there is an uncertainty in the energy of the excited nucleus. Therefore, corresponding to this uncertainty in energy, there will be an uncertainty in the frequency of the gamma ray also, right? So we have to calculate the uncertainty in the frequency, uncertainty in the frequency, uncertainty in the gamma ray frequency. Okay, so uncertainty in the gamma ray frequency can be easily calculated. So the frequency uncertainty can be calculated like uh, um, 10 raised to 6, that is that is the, we have the energy uncertainty. From here we can consider the frequency uncertainty, because you already know that E is equal to h nu. Therefore dou E is equal to h into dou nu, or the frequency uncertainty dou nu is equal to, okay, is equal to h divided by delta E, h divided by delta E, that is equal to 6.625 into 10 raised to minus 34 delta nu is equal to, delta nu is equal to delta E divided by the uncertainty in energy divided by h, that is equal to 10 raised to minus 27, 10 raised to minus 27 joules, that is uncertainty in energy, divided by what? Planck's constant. Planck's constant is equal to 0.6 into 10 raised to minus 33, right? 10 raised to minus 33 joule second. So that is equal to, okay, that is equal to, that is almost equal to 10 raised to 6 hertz, 10 raised to 6 hertz. Okay, so that is the uncertainty in the frequency. So there is an uncertainty in the energy. Corresponding to that uncertainty in energy, there is an uncertainty in the frequency, and this uncertainty in the frequency is 10 raised to 6 hertz. Okay, that is delta nu, uncertainty in the frequency. So initially, we thought that this frequency is a very finite frequency. What was that finite frequency we calculated? That is 3.5 to 10 raised to 18 hertz. That we thought that that is a very finite frequency. This one, 3.5 into 10 raised to 18 hertz. Now we have proven that that is not a finite frequency, but there is an uncertainty of 10 raised to 6 hertz, right? So what is the relative line width? If it was emitting a frequency of 3.5 to 10 raised to 8 hertz, the spectrum would look like this. Okay, the spectrum would be like this. That is 10 raised to 18 hertz. Okay, so it would be a sharp line in the spectrum. But we have proven that that is not going to be a sharp line. Instead of that is going to be a band like this, because there is an uncertainty, and that uncertainty is 10 raised to 6 hertz. So we will get a line width, and that line width is almost 10 raised to 6 hertz. Okay, so instead of getting a sharp frequency, we will get a band, and the line width is almost in the range of 10 raised to 6 hertz. So what about the relative line width? Relative line width. The relative line width. The relative line width is 10 raised to 6 hertz divided by the original frequency, that is almost 10 raised to 18 hertz, right? 10 raised to 18 hertz, and therefore the relative line width is almost 10 raised to minus 12 hertz, not hertz, almost 10 raised to minus 12. And I just calculated this just to show that this is very small number. Okay, so you convert it to almost all the spectroscopic technique, the relative line width here is very small. So that's what I said, the frequency uncertainty is almost negligible compared to the frequency of the gamma ray. Okay, so still it has some value. Okay, there is a frequency uncertainty that I wanted to ultimately say, and therefore you will see a broadening of the line because of the frequency uncertainty. So what is the consequence of this one? Okay, so if the iron nucleus, the sample iron nucleus, the sample iron nucleus can absorb any range of frequency which will fall inside this band. Okay, so that is what we have to understand. It is not necessary that the sample nucleus should receive 10 raised to 18 hertz exactly. That is not necessary, or 3.5 into 10 raised to 18 hertz necessary. If the sample nucleus is getting 3.5 into 10 raised to 18 hertz, that's fine, it will be absorbed, no problem. But also it will absorb a range of frequencies, and whatever range of frequencies that are falling inside this band, all these range of frequencies can be absorbed by the sample nucleus, and then it will be going to the excited stage. Okay, so that is what I just wanted to say. The sample nucleus can absorb a range of frequencies because of the uncertainty in the energy of the excited nucleus. Okay, now this is one thing that we have to consider. Now we may be thinking like, okay, we have not proven why the sample nucleus here was not absorbing the gamma ray coming from the cobalt source. Okay, we are just digging into the reason of that. We just understood that there is a frequency uncertainty. And now we have to consider the next fact. The next fact is that we have to consider the momentum of the emitting photon. Momentum of the emitting photon. Momentum of the emitting photon. Photon means the gamma ray photon. So from de Broglie's relation, we can calculate the momentum. Okay, the momentum P is equal to h divided by lambda. We already know this from the de Broglie relation. That is equal to h divided by c divided by nu, because lambda is equal to c by nu. and that is equal to h nu divided by c, right? So we can calculate the momentum of the photon, gamma ray photon, which is being emitted from the cobalt source. Okay, so that momentum will be equal to h is equal to 6.62 into 10 raised to minus 34 kilogram meter square second raised to minus 1. Okay, that is, instead of joule second we can write it like this also, kilogram meter square second raised to minus 1 into nu is the frequency. Okay, the frequency is 3.5 into 10 raised to 18 hertz, 10 raised to 18 hertz, even though there is an uncertainty in this energy. Okay, because that uncertainty is very small compared to the frequency of this one. We have already proven that, because the relative bandwidth is very small, 10 raised to minus 12. So I'm writing this as 3.5 into 10 raised to 18 hertz for the calculation. Okay, divided by the velocity of light, that is 2.99 into 10 raised to 8 10 raised to 8 meter per second. Okay, so if you are solving this, we will get almost 7.74 into 10 raised to minus 24 kilogram meter second raised to minus 1. Okay, so this hertz you can write it like a per second also. Okay, then everything is fine. So this is kilogram meter second raised to minus 1, because 1 meter from here and 1 meter from here will be cancelled, and second inverse from here and second inverse from here will be cancelled. So what is remaining is kilogram meter second raised to minus 1. Why? That's why it has this unit. So that is a unit of the momentum. Okay, because momentum is equal to mass into velocity. Kilogram is the unit of mass, and v has the unit meter per second. So the momentum has the unit kilogram meter per second. So it's the same unit we have got from got here also. So momentum of the photon is 7.74 into 10 raised to minus 24 kilogram meter second raised to minus 1. What is the consequence of this momentum of the photon? The photon has a momentum, and what's the consequence of this one? If you are firing a bullet from a gun, okay, and that bullet will have a very large momentum, and the momentum should be conserved, and therefore you will see that when the bullet is being fired from the gun will go back, right? The gun will move a little bit back. You have seen that in the movies, right? When the soldiers are firing, you can see that the gun is moving back, and that is called the recoil of the gun, right? Recoil of the gun. The same is happening here also. We have a source here, source of the gamma ray, and from here the gamma ray photons will be emitted, and this photon is being emitted with a momentum of of 7.74 into 10 raised to minus 24 kilogram meter per second. Since it is going with a momentum, then the source should recoil. That is what we have to expect. Like the gun is going with a momentum, the bullet is going with a momentum, then the gun will have a recoil. Okay, like that we have to expect that the source will have a recoil here. So we can calculate the recoil velocity of the source, with which velocity the source is moving backward when the photon is moving to the front. Okay, so we can calculate this from the recoil velocity calculation. You already know that the recoil velocity calculation is m1 v1 is equal to minus m2 v2, where m1 v1 is the momentum of the source and m2 v2 is the momentum of the photon. In our case, or in the case of a gun, you can calculate it, you can think it like m1 v1 is the momentum of the gun and m2 v2 is the momentum of the bullet. Okay, in our case it is source and photon. Okay, so this momentum is conserved, that is why m1 v1 is equal to m2 v2. Both of them will have a different direction of the velocity, that is why the sign are different. Okay, so in other words, we can write it like momentum P1 is equal to minus P2. Momentum of the source is equal to the negative of the momentum of the photon. Okay, from this one we can write it like momentum of the photon is 7.74. Okay, so P1 is equal to momentum of the source is equal to momentum of the photon, that is minus 7.74 into 10 raised to minus 24 kilogram meter second raised to minus 1. We can write it like this, right? And from here we can calculate the velocity of the source. So velocity of the source v is equal to, or v1 is equal to, I'm going to calculate the magnitude of the velocity. Okay, and that is equal to 7.74 into 10 raised to minus 24 kilogram meter second raised to minus 1 divided by mass of the source. Okay, mass of the source. The mass of the source is almost, in our case, source is, what is the source? That is excited ion nucleus is the source. That is around 9.4529 into 10 raised to minus 26, 10 raised to minus 26 kilogram. That is the mass of the Fe57 nucleus, and the answer is around 0.819 into 10 raised to 2, 10 raised to 2 meter per second, or 0.8 we can calculate, we can count it as 1 because it is almost equal to 1. So this is approximately equal to 10 raised to 2 meter per second. So what do you understand from here? From here we can understand that when the photon is photon is being emitted, the source nucleus will have a recoil, and that recoil velocity is 10 raised to 2 meter per second. It's a big velocity, right? 100 meter per second. In 1 second it can move backward about 100 meters. Okay, so the source is moving with a big velocity. Now, what is the consequence of this recoil of the source nucleus? Recoil velocity of the source nucleus. Now, let me say an example. You are standing in a railway station, okay, and an engine is coming from a distance through the track, and the engine is coming towards you. When the engine is coming towards you, sounding the horn, what you will hear? Are you going to hear the same pitch? No. When the engine is moving towards you, the pitch of the sound is increasing, and when the engine passes you, the pitch of the sound is decreasing. Why it is happening? That is because of a change in the frequency, because of the movement of the source. Okay, you are standing here, okay, and the source is moving towards you. When the source is moving towards you, this is engine, okay, engine is moving towards you, and when the engine is moving towards you, what is actually happening? It is producing the sound waves. Okay, the sound waves is moving like this, sound wave is like this. Okay, so how many are there? 1 2 3 4 5 6 7 8 9 10. Okay, so the engine is producing the sound. Suppose that the engine is at a rest, then what you will hear? You may be hearing that maybe in 1 second. I am just saying a typical example. In 1 second, through your ear, or through passing your ear, 10 waves will be passing you. Okay, 10 waves will be passing you in 1 second. Okay, so you will hear a particular frequency, and that particular frequency is 10 cycles per second. Okay, so, or 10 waves per second. And if, what will happen if you are moving a bit towards the engine, okay, or you are moving a bit towards the engine, what you are going to do is you are going to cover two more waves. You are going to cover two waves in advance. Therefore, what will happen is that if you are staying here and the engine is also staying here, then you would hear actually 10 waves per second. But when you are moving towards the engine, actually you are jumping towards the engine, and you are additionally covering two more waves. So instead of hearing 10 waves per second, you will hear 12 waves per second. Okay, 12 waves per second, because you are moving towards the source. Or you can you can think reverse. You are moving away from the source. You are moving away from the source. You are going two step here, so that when the sound is coming towards you, you are going away from here. What will actually happen? What will actually happen? If you are moving away from here, the 10 waves cannot come to your ear in 1 second, because the waves again has to pass some time, right? So maybe it will reach only 8 waves per second in your ear. So if you are moving away from the source, only less number of waves will reach your ear in 1 second, because you are moving away from the source. So you will hear a less frequency if you are moving away from the source. Okay, now I was talking about your movement, means the receiver's movement. You can think the reverse also. If the receiver is at rest and if the source is moving, okay, and if the source is moving towards you, the relative distance between you and the source is decreasing. In that case, you will hear an increased you will hear an increased frequency like a 12 waves per second. Okay, and if the relative position between you and the source is increasing, means the source is moving away from you, then you will hear only a decreased frequency, and this is called the Doppler effect. Doppler effect. Doppler effect. The same thing is happening here also. Okay, and here we know that when the photon is being emitted by the nucleus has a recoil velocity, means the nucleus is moving. Nucleus is not at rest, and because of this movement of the source nucleus, the frequency felt by the receiving nucleus will be different. Actually, the source nucleus was emitting a frequency, and that frequency was 10 raised to what was that? 10 raised to, we calculated here, 10 raised to 18 hertz here, and it had a line width of 10 raised to 6 hertz. So we should expect that this should fall in this line width, that is, the emitting frequency should fall in this line width. And if the receiver nucleus is receiving any frequency within this line width, it should receive that nucleus and go to the excited state. But what is the consequence of the recoil velocity? Because of the recoil velocity, there will be a Doppler shift. There will be a Doppler shift. And Doppler shift is the receiver is feeling, or receiver is experiencing a shifted frequency. And we can calculate this shifted frequency. Okay. And this shifted frequency delta nu, that is the Doppler shifted frequency delta nu, is equal to nu into V divided by C hertz, okay, or per second, where nu that is the frequency of the emitter radiation, frequency of emitted radiation. In our case, that is 3.5 into 10 raised to 18 hertz, and C is the velocity of the emitted radiation, velocity of emitted radiation, and V is the recoil velocity. Okay, recoil velocity. So if you know the frequency of the emitted radiation and velocity of the emitted radiation and the recoil velocity of the source, then we can calculate the Doppler shift. Doppler shift is the the shift in the frequency experienced by the sample nucleus. Okay, so this Doppler shift delta nu is equal to, I am going to substitute for nu v and c. Okay, nu is equal to 3.5 into 10 raised to 18 hertz, 10 raised to 18 per second into v. V is the recoil velocity, and recoil velocity is 10 raised to 2 meter per second that we calculated, divided by the velocity of the emitted radiation. That is electromagnetic radiation, and the electromagnetic radiation will go with a velocity of 2.99 into 10 raised to 8 meter per second. So from here we can calculate the Doppler shift, and this Doppler shift is almost 0.95 into 10 raised to 12 per second, and that is almost equal to 10 raised to 12 per second. Okay, so that is the shift in the frequency due to the recoil of the sample nucleus. Shift in frequency due to the recoil of the sample nucleus. Where did we expect the frequency? At 3.5 into 10 raised to 18 hertz. That was the frequency emitted by the source, and this frequency will have a line width of 10 raised to 6 hertz. Okay, that also we know. But we have seen here that the emitted frequency will be shifted by a factor of called a Doppler effect, and that shifted frequency is 10 raised to 12 per second, or 10 raised to 12 hertz. That's a huge shift if you are comparing the line width, right? Because the line width is 10 raised to 6 hertz. So the shifted frequency is 10 raised to 12 hertz, means it is it is shifted to a very large distance compared to the line width. Okay, so it is very large compared to the line width of 10 raised to 6 hertz. So what will be the frequency spectrum if you are considering? So we consider that the frequency should be like this. So if we are taking the spectrum, so here is the 10 raised to 8 hertz frequency coming here with the line width of 10 raised to 6 hertz. 10 raised to 6 hertz is the line width. Okay, this is 10 raised to 6 hertz, and it is almost coming at 10 raised to 18 hertz. Okay, and because of the Doppler shift, it has shifted to 10 raised to 12 hertz. So it is not falling anywhere in this line width. It will be falling at a lower frequency, like somewhere here. Okay, the shifted frequency will be somewhere here. Okay, so the shifted frequency is because of the Doppler effect. So what will happen if the sample nucleus is placed in the way of this gamma region? The sample nucleus can absorb any frequency which is under this band, because this is the frequency required for the sample nucleus to be excited to make a transition to its own excited state. This is a frequency. Okay, any frequency within this band. But where is the actual frequency it is receiving, or what is the actual frequency felt by the sample nucleus because of the Doppler shift? And that actual frequency will come under this band, like this band. Okay, so that if this is the frequency the sample nucleus is experiencing, or this is the frequency of the photon hitting the sample nucleus cannot absorb that frequency, and it cannot go to the excited state, because the excited state frequency, the frequency corresponding to the difference between the excited nucleus and the ground state nucleus is falling in this band, but the nucleus is receiving a completely different frequency because of the Doppler effect. And that is why I said in the beginning, if the nucleus is placed in the way of the gamma region, placed in the way of the gamma ray which is being emitted from here, that is not going to absorb that gamma frequency. This is the reason. Okay, now you understood why the gamma ray frequency is not absorbed by the nucleus. Actually, this prevented the earlier study of the gamma ray spectroscopy. Okay, the sample nucleus is not absorbing, so the scientists were amused why the sample nucleus are not absorbing the gamma ray. It should actually absorb, but it is not absorbing. The reason was not clear in the beginning, and it is here the Mössbauer, the famous scientist Mössbauer, contributed most of his insights. Okay, Mössbauer explained why it is not happening and how this phenomenon can be harvested in order to develop a useful spectroscopic technique. So, what Mössbauer did is, Mössbauer understood that it is because of the recoil velocity, the sample nucleus is not absorbing the gamma ray. So Mössbauer thought that somehow this recoil velocity should be minimized, okay, or the sample nucleus recoil should be stopped. If the recoil velocity is minimized, or in the ideal case, if the recoil is stopped, so that the recoil velocity is 0 meter per second, in that case, then it is going to emit a gamma ray which will fall under this region, okay, around 10 raised to 18 hertz with a line width of around 10 raised to 6 hertz. That is what Mössbauer understood. So he thought how this recoil can be stopped. For that, Mössbauer used a solid lattice of cobalt 57. What is peculiar with the solid lattice? Inside the solid lattice, the atoms are fixed, right? The atoms are fixed. The movement of the atoms are restricted under the solid lattice. You already know this. So he used a solid lattice where the movement of atoms are restricted, minimal movement within the lattice. The thermal motion of the lattice atoms are reduced to minimum. Okay, and in order to ensure that this thermal motion of those lattice atoms are very much reduced, he used very minimum temperature also. Minimum temperature. You can use liquid helium or liquid nitrogen like that. So if you are using a very minimum temperature, if you are operating at very minimum temperature, whatever possible, okay, then the thermal motion of these lattice atoms will be minimized, restricted, so that the recoil velocity can be stopped. The recoil of the sample nucleus can be stopped. No, the source nucleus can be stopped. So if the recoil of the source nucleus is stopped, then the gamma ray will be emitted and it will fall in this region, right? Around 10 raised to 18 hertz with a line width of 10 raised to 6 hertz. It will fall in that region. So Mössbauer did that. He used a cobalt 57 solid lattice, and from here the gamma ray will be emitted. Then he used the metallic iron, and he used a and then he placed a Geiger counter behind that. Then he saw that there is a fall in the Geiger counter reading. And why there is a fall in the Geiger counter reading? Because the metallic ion absorbed the gamma ray which was coming from this solid cobalt 57 lattice. So you have to understand that even if it is solid cobalt 57 lattice, the lattice atoms which are cobalt 57 at this moment, maybe in the next moment will be converted to iron 57 because of the radioactive disintegration, right? So actually, even if you are using the cobalt 57 lattice, the source nucleus is iron 57, okay, and that will be in the lattice position of the cobalt, and its movement will be restricted also. So it will emit a gamma radiation which is falling under the expected band, okay, here, and that will be absorbed by the metallic ion, and that will be recorded in the Geiger counter. That was it is an important observation by Mössbauer. Now what he did is that in the case of metallic ion it worked, The Geiger counter was showing a fall in the reading, but instead of the metallic ion, Mössbauer also placed other samples which contain iron. For example, FeCN 6 times, FeCN 6 times. Okay. In this case, if he is using FeCN 6 times, okay, and in this case, that is actually K for FeCN 6 times 2 minus. Okay, this is so in this case, the ion is in the +2 oxidation state, right? Because that is 2 plus. Sorry. Yeah, no, 2 minus. Yeah, okay. So ion is in the +2 oxidation state. Potassium will have 4 positive charge, and iron will have a 2 positive charge. Total there are 6 positive charge, and this 6 positive charge will be neutralized by 6 cyanide ligands, right? So this is okay for FeCN 6 times. Actually, this Fe okay for FeCN 6 times. Um, yeah, only the complex ion has the charge of 2 minus. Okay, and no. Complex ion will have a charge of 4 minus. I am very sorry, my brain is not working. Okay, that is why it will be neutralized by the potassium. Okay, so if you are placing a sample like this, okay, then this ion is not going to absorb. This ion is not going to absorb the radiation coming from here. Okay, then why the ion in this sample is not going to absorb the radiation coming from here? This is because the iron atom here or iron nucleus here is in a different chemical environment, right? So it is in the clutches of the ligands, and therefore there is a different chemical environment, and this chemical environment is sufficient enough to bring a change in the nuclear energy levels. Okay, so the chemical surrounding here is sufficient enough to bring a change in the nuclear energy levels. So we should not expect that the same the difference in energy between the ground state and excited state of the sample nucleus, of the source nucleus delta I. This we already know. Okay, that is we already calculated this as 1.5 raised to what was that? No, 2.30 into 10 raised to minus 15 joules. Okay, 2.30 into 10 raised to minus 15 joules. That was energy difference between the excited state and the ground state of the source nucleus. And we should not expect that this is the same in the case of this iron nucleus, because this iron nucleus is in completely different chemical environment, and therefore this iron nucleus will have a completely different excited state and ground state. So this delta E, in the case of the sample iron nucleus, which is in a different chemical environment, will be different from the delta E which is for the source. If you are calling this as delta E1 and if you are calling this as delta E2, we can see that delta E1 is not equal to delta E2. Okay, and this is because of the chemical surrounding. And that is why if you are placing the metallic ion here, that metallic ion will absorb the frequency, because in the case of metallic ion it will be equal to the difference in the excited state and the ground state as in the case of the source. But if you are placing an ion which is a part of the chemical compound, in that case the delta E will be different, therefore this frequency will not be absorbed. So how the frequency emitted from the source can be absorbed by the sample ion nucleus? Is there any way? Actually, Mössbauer's the contribution comes here. Mössbauer thought that the Doppler effect, which earlier prevented the study of the gamma ray spectroscopy, now comes as a blessing. The Doppler effect is a blessing rather than a nuisance. Earlier, it was thought that the Doppler effect is a nuisance because it prevented the study of the gamma ray spectroscopy. Now, Mössbauer thought that this Doppler effect is a blessing. It is a useful thing. How it is going to be useful? I will explain how Mössbauer utilized this Doppler effect in order for this sample nucleus to absorb the frequency emitted from the sample the source nucleus. Actually, we calculated that if the recoil velocity is 10 raised to 2 hertz, okay, if the recoil velocity is 10 raised to 2 hertz, then it can bring about a shift in the Doppler shift of around 10 raised to 12 hertz, right? Doppler shift. This is the recoil velocity, and this recoil velocity can bring about a Doppler shift of 10 raised to 10 raised to what was the Doppler shift? 10 raised to 8. What is it? We calculated just above. Yeah, 10 raised to 12. 10 raised to 12 hertz. 10 raised to 12 hertz, not 10 raised to 8. 10 raised to 12 per second. Okay, this is meter per second. So this velocity 10 raised to 12 meter per second can bring about a Doppler shift of 10 raised to 12 hertz. Okay, and what about if you are applying the same calculation as we did here? What was that calculation? And that is delta nu is equal to nu into V divided by C. Okay, this calculation. That is the calculation for Doppler shift. If you are calculating this Doppler shift of a recoil velocity of around 1 centimeter per second, 1 centimeter per second. 1 centimeter per second is equal to 10 raised to minus 2 meter per second, right? So if you are calculating the Doppler shift corresponding to 1 centimeters per second, and that Doppler shift will be, what about that Doppler shift? You can substitute 10 raised to minus 2 meter per second in this calculation. Okay, instead of 10 raised to 2, you can calculate 10 raised to minus 2. If you are substituted 10 raised to minus 2 here, you will get around 10 raised to 10 raised to 8 hertz, right? 10 raised to 8 hertz. 10 raised to 8 hertz. So if there is a Doppler, and there is a recoil velocity of 1 centimeter per second or 10 raised to minus 2 per second, then the Doppler shift will be 10 raised to 8 per second. That's good, right? What does it mean? If we are moving the source, our source is a cobalt lattice in which the source nuclei are at rest, almost at rest. So if these source nuclei are moved at a velocity of 10 raised to minus 2 meter per second or 1 centimeter per second, that is going to bring a Doppler shift of 10 raised to 8 per second. Okay, so if the source nucleus is at rest, then you should expect that there should be a band around 10 raised to 18 hertz, and this bandwidth is 10 raised to 6 hertz. Okay, if this source nucleus is moved at a velocity of 1 centimeter per second, that should bring a Doppler shift of 10 raised to 8 hertz. 10 raised to 8 hertz is 100 times of this line width, right? So it should come somewhere here. it is 100 times of this line width. It should be somewhere here. My scale is not very good, but what we understood that it will shift to here. And if you are moving if you are moving the source in the reverse direction, means if it is 1 centimeter per second, next in the next time you can take a velocity of minus 1 centimeter per second. Minus 1 centimeter per second means you are moving the source in the reverse direction. Then the Doppler shift will take the frequency to the other side, so it will fall somewhere here. So what we have to understand here, just by moving the source at 1 centimeter per second velocity, that's a very small velocity, right? In 1 second it is moving only 1 centimeter. Okay, that velocity can be easily attained in the laboratory conditions. So the technique can be very simple. So if we are moving at this velocity, we can cover a very good range from here to here, right? So you have to do 100 scans, like 1 centimeter per second, then 0.99 centimeter per second, 0.98 centimeter per second, like that. You can do 100 scans or 200 scans, or you can do 100 scans in both directions, to and fro. Then it will cover an entire region. You can get all region here, right? The if you are doing at a very if you are scanning at a different velocities ranging from 1 centimeter per second to minus 1 centimeter per second, it will cover the entire region. So actually, the iron nucleus which is in the sample should should absorb any frequency within this, right? We are scanning over the entire region. So suppose the iron nucleus is ready to absorb this region. So we are scanning from here to here, and when the scanning comes here, there will be a drop in the Geiger counter, drop in the reading of the Geiger counter. Then it means that the iron sample, okay, sample means the, for example, K for efficient 6 times. Okay, this sample will absorb this radiation. So in order to get the range of the radiation, range of the frequency which is being absorbed by the sample, we can use the Doppler effect. By Doppler effect, we can cover a broad region. Okay, and within this broad region, somewhere the sample absorption frequency will fall. Okay, so the Doppler effect comes here as a blessing. We can utilize the Doppler effect. And how we can do this in the laboratory? For example, you can mount the source in the edge of a screw. You have a screw here, okay, a screw, and the edge of the screw you can mount the source. This is the source, okay, and this screw can be rotated both clockwise and anti-clockwise. Okay, if it is rotated in the clockwise direction, then this will move towards here. If the screw is rotated in the anti-clockwise direction, the screw will move backward, right? You already know this. So the source can be moved forward and backward just by rotating the screw at a constant velocity at a time. Okay, so adjusting the cycles per second of the movement of the screw, you can adjust the velocity, and then you can cover a range of velocities at a different source velocities, range of frequencies at a different source velocities, and then you can find out the exact frequency range where the sample will absorb the gamma ray frequency. In another technique, you can use a loudspeaker coil. Okay, loudspeaker coil like this. Here is a disk, and in this disk you can mount the source nucleus. Okay, and then you can give an AC frequency here. What will happen if an AC frequency is given here, and this loudspeaker coil will actually move back and forth, right? It will move to here, then it will move to here. Okay, so it will move back and forth, and you can see that when you are giving a particular AC frequency, the how much it will move back and forth depends upon the AC frequency, and then in the edge, okay, when it is in the edge, it is moving here, and then it is moving backward and moving to here. Then it is coming back and come to here. Then it is again moving back and come to here. So it will have it the sample will come to rest when it is in the extreme position. When it is here, the sample will come to rest, and when it is here, then also the sample will come to rest. And from here to here, when it is moving to here, the velocity will slowly increase, and the velocity will be maximum when it is in the midpoint here. Okay, then the velocity will again decrease, and then it will come to rest. And when it is moving to the other side, the velocity will slowly increase, and when it reaches the midpoint, the velocity will increase, and when it reaches here, the velocity will decrease. So if you are using a loudspeaker coil, we can get a range of velocities for the source nucleus. And if we are connecting this to a multi-channel computer, that multi-channel computer will record all the source velocities at every point, and also it will record the count, the reading from the Geiger counter, for example. Okay, so the multi-channel computer can detect at which position, which position of the source, and at which velocity of the source, what is the absorption of the radiation. Okay, so this is much more similar than this one. So this can be electronically controlled, and the multi-channel computer will give the information. Okay, so we have the source here, then we have the sample here, then we have the Geiger counter here. Okay, Geiger counter here, in this case also we have the sample here, and then we have the Geiger counter here, and in this case we are moving the source towards the sample and away from the sample just by rotating the screw. And here it is much more complicated body, but it is more easier that we are using a loudspeaker coil and we are giving a particular AC frequency. Then this will move forward and backward at different velocities, and the multi-channel computer will detect the velocity at every position, and also it will take the reading from the Geiger counter. Okay, so finally we will get a spectrum, and the spectrum will read the millimeter per second, that is the source velocity against the counts per second. Okay, so in this one we have counts per second, and here we have millimeter per second. Okay, and then at a particular millimeter per second means at a particular source velocity, then we will see a spectrum like this. That means that the Geiger counter will show a fall in the count, means the sample has absorbed when the source velocity is this one. Okay, so for different iron from different chemical samples, this will be different, because the chemical surround is going to determine the difference in energy between the excited state and the ground state, and depending on that, different samples will give different positions in this spectrum. So this is an excellent way to determine in which oxidation state the metal is, or what is the ligand field around the metal, and all these things can be predicted from this Mössbauer nucleus, because the oxidation state of the metal, the ligand field of the metal, and all these things are going to affect the nuclear energy states, and corresponding to that there will be a shift in the spectrum. Okay, so the Mössbauer spectroscopy is a very powerful technique, especially in the case of the iron samples. It's a very powerful spectroscopic technique in order to predict the oxidation state, spin state, ligand environment, etc. So this is how the Mössbauer spectroscopy is working, and this is the core principle behind the Mössbauer spectroscopy. Okay, I hope you understood this. And if you have any doubt, please don't hesitate to ask me. And in the next video, I will cover the topic like a chemical shift and the quarter pole effects. Thank you for watching and stay tuned.